Hi everyone, this is the first part of your introduction to lab for the week of October 12, and we'll be looking at exercise 18 from your lab book for this part of the lab introduction. We're going to use the orbit of a satellite around the moon to determine the mass of the moon. And the way we do that is laid out for you in the introduction right here. You should read the introduction fairly carefully to this lab. It's pretty short. But we've been using in class, and we're accustomed to saying that Kepler's third law is that the period of orbit squared is equal to the semi-major axis cubed. But that's only true, absolutely only true, if we're talking about the orbit of a planet or some object like a planet around the sun. So if it's the object, if it's the orbit of an asteroid or a comet or the planet around the sun, we can use this, and we have to have the semi-major axis in astronomical units and the period in years. But for this lab, we can't use that because we don't have any of that stuff. We have the orbit of a satellite around the moon, and we're going to determine the mass of the moon that way. Now, we can do this by using the so-called Newtonian form of Kepler's third law, and we could derive, if we were in introductory physics class, we would derive this Newtonian form of Kepler's third law. It's actually pretty straightforward to do, but it's written for you there on page 147, where you have the mass of the object that's doing the orbiting plus the mass of the object that's being orbited times p squared is equal to 4 pi squared divided by Newton's gravitational constant times the semi-major axis cubed. Now we don't want things in years and astronomical units because we got to make sure our units match all the way throughout here. Now, if we're talking about something small orbiting something larger, then the something small orbiting something larger, if it's very small relative to the larger thing, we can just get rid of that, and we can get the mass of the thing that's being orbited that way. Or we can plug in the mass of the thing that's doing the orbiting if we want to. But we don't need to if there's a very big difference in mass right there. So you need to think about whether that applies to this activity or not. So that's what we're looking at, is using the Newtonian form of Kepler's third law to think about measuring the mass of the moon. So we'll walk through the steps of the activity right here, the steps of the exercise. And in step 1, it says to plot the data that shows up in this table and plot it on this graph right here. Now, if you don't want to be plotting in your lab book, you can print out graph paper from someplace online. I put a link on the Katie site to some online graph paper. I don't know if it's a good site. I don't know anything about it. I just did a Google search and found it and put it there. You can find your own graph paper if you want to and print it out and use it. I don't care if you don't use the graph paper. If you use Excel or something like that, that's a-okay by me. So however you want to make the graph, but you want to graph this data and the data that appears in the table back here. And that data is the position. So here's the satellite out there orbiting the moon. And that data is the position of the satellite that's being telemetered back by the satellite. So we've got the position at different times. You can read the time, and you can read the x-coordinate of the orbit and the y-coordinate of the orbit. You see the time is in 15-minute intervals. It tells you every 15 minutes where the satellite was in orbit. And then you can get the x, y positions that you can plot on your graph paper right here. Note that those x, y positions are in lunar radii. So you need to know the radius of the moon. And the radius of the moon is given to you at the bottom of page 149. So if you know the radius of the moon, then you can determine that in kilometers, for example. But this graph's set up so you can measure this in lunar radii. And so now what you'll take is you'll take the moon to be at one focus. Just sort of assume that's true and just start trying to work from there. And to say if the center of the moon is at one focus, that means the moon could appear on your graph with the focus at 0, 0, and the surface of the moon is going to be 1 lunar radius away from that. That's how far the surface of the moon is away from the center of the moon. So you'll get that graph of the center of the moon there, the moon on your graph. If you can draw it on there or not draw it on there, if at any point your satellite gets within 1 lunar radius of the center of the moon, you've made a mistake and your satellite has crashed into the surface. So you need to be aware of what's going on there and see that sort of thing. But you should be able to draw an ellipse. You have all of these points, and you can draw an ellipse, and you can say the center of the moon is one focus of the ellipse. Okay, so that's what you're doing, is you're plotting those points, and you can do that electronically, or you can do that by hand on paper if you want to. And then you want to verify Kepler's first law, is what the first step says. And Kepler's first law says the distance from one focus to any point on the ellipse to the other focus is the same. Now, I recommend doing this at least twice. Measuring those distances. And I also recommend, if you really want to convince a reader that you know what you're doing, then you shouldn't make two drawings that look like that are symmetrical, that look identical. Make one that looks very different from the others. Okay? And so try some different paths and see if those links are the same. Now, in order to do that, you're going to have to know where the major axis is and where the other focus is. So if this is one focus, what you can do is you have all of these points out here. Use the fact that the major axis is going to be the longest line you can draw through the focus. You got to go through this focus and draw a line that is the longest line you can draw through that, and the other focus is going to be the same distance in on the opposite end. And so now you can be able to plot both foci and the major axis on your graph right there. And that's what we want to do in part one. You want to plot the focus, the foci on there, and draw a line through those foci that is the longest distance between that you can draw on there. That's going to be your major axis. Now, the major axis, recognize that the longest line that you can draw that connects with the orbit of the satellite may not hit one of your data points. It may land between two of your data points. So you can twiddle around. If you have a ruler, you take a ruler and you can just measure. I can just get in with my ruler here, and I can measure and say, where's the longest line that I can draw? That's short, getting longer, getting longer, getting longer, getting longer, getting longer, getting shorter, shorter, longer, shorter, boom, longest line I can draw through there. Okay, so you can do something similar like that, is to draw the longest line that you can get through there, to call that the major axis. Measure the distance in to get the focus. So in part one, that's all you're doing. Step two, it says find the semi-major axis, the minor axis, the semi-minor axis, the eccentricity, and the period of orbit. Now, what you want to do here is to recognize that what you've drawn in your graph is a scale model of the orbit. It's not the orbit. The orbit is the actual satellite in orbit around the actual moon. So that's what this question's at. Step two is asking you for those things, those properties of the actual orbit of the actual satellite around the actual moon, not on your model. So I don't care how long this line is on your model, because you could, mine's bigger, I could draw this whole board, and I could make my ellipse look like this, or my ellipse look like this, and I can have different size lines, and that different size just is determined by the scale of my model. And the scale of your model is that one lunar radius, 1,738 kilometers, is equal to one big box on your graph from 0 to 1. So each box is equal to that. So you can do a conversion to say this many kilometers, the radius of the moon is equal to however many centimeters or millimeters or whatever you want in there along that. And you can say, that's the scale of my model. So if I get 2 lunar radii to be 2.3 lunar radii to be my to be my major axis, you can measure your major axis in lunar radii, or you can measure your major axis in centimeters or millimeters or whatever unit you're using, and say, okay, I measure 17.3 centimeters to be my major axis on here, but 17.3 centimeters on this graph in this scale model, 17.3 centimeters is equivalent to X number of kilometers. And you can report the semi-major axis of orbit in kilometers that way. And so that's what we want to do in this part. For the orbit, you just have to remember the orbit is where the thing wraps back around, completes one loop around there. Can you figure out how long it takes to complete one loop around there by looking at the data? You should be able to do that. And then the eccentricity, remember, is the distance between the foci divided by the whole distance of the major axis. Now, there's no need, as long as you use the same units. If you say eccentricity is one distance between the foci divided by the major axis, all of the major axis. As long as the major axis and the distance between the foci are in the same units, you get the eccentricity. So there's no need to convert to physical space units to get the eccentricity out of that. So far, so good. You can report on all of the properties of the orbit that way. And then you can move on to step 3 and show that Kepler's second law is valid. Now, for Kepler's second law, you want to do something like this, except it's an area thing. And so you need to make some estimation that says a line connecting the satellite to the moon, the center of the moon, sweeps out an equal area in an equal amount of time. So you can look between a few data points right there, and you can estimate that area. You can estimate that area by treating it as a triangle, or treating it as a couple of triangles, or just by counting boxes that are inside that space right there. If you can count the number of boxes that are inside that space and estimate what they are, you can get the area. Now you might look, if you blow that up, it might look something like this. There's a triangle, and you can do half the base times the height is the area, but it's not quite a triangle because it's got that little bit that's held on right there. You can treat that as another triangle and add another area in there, and if you maybe you fit a third one, I don't know, but you can try different things to try those areas. And again, one when it's close and moving fast, and one when it's far away and moving slowly is going to be more convincing to a reader than two of them that look the same here. And so this is where you're trying to figure out if it sweeps out equal area in equal time, and you should be able to do that sort of thing. You might find it useful. I don't know if you'll find it useful or not to do S equals R theta and try to figure out what that theta is, or remember 57.3 theta is equal to S over R times 57.30. We figured out if you're in degrees. And to measure that along there, you're on your own there to try to figure that out, whatever you think the best technique is. And then using Kepler's law, and the data that's at the bottom of 149. So the Newtonian form of Kepler's law and the data that's at the bottom of 149, you should be able to determine the mass of the moon. So you go back, I've erased it now, but you go back to the Newtonian form of Kepler's third law that's at the introduction of the lab and say, here's what I calculate to be the mass of the moon. Go ahead and compare that to the accepted mass of the moon and see how you did and work back on that. So really to do this, you probably really just need a ruler. So if you have access to a ruler, you can do this at home. And I think we'll try to do this as an at-home lab this week. So then I'd like, when you're done, answer those 3 discussion questions. So what you turn into me is a sheet that shows all the work and all the calculations that you did and the answer to all of the questions, the report of all of that stuff that was in steps 1 through 4 that we just talked our way through. I want to see your graph. I want to see your graph. I want to see all the work that you're doing to do all these calculations, and I want to see all the things that were asked for in steps 1 through 4, like the semi-major axis and the mass of the moon and all of that, and do the comparisons to the actual mass of the moon at the end would be great. And then you can answer all 3 discussion questions. You can answer all 3 discussion questions, turn in your graph, and turn in the data, the calculations that you've done in steps 1 through 4 along the way, and we'll be in good shape. So that's what we got for the mass of the moon. We're also going to do exercise 21, but we will have a separate video for that one. So take care, everybody. We'll see you again soon.